This is our last and final chapter. It's about the chemistry of coordination compounds. So we've done a little bit of organic, a little bit of biochem, and now we're going to do a little bit of really what's inorganic, or compounds that are more based around transition metals and things like that. So organic is really all the carbon and nonmetals. And then inorganic is a lot more have to do with what are called coordination compounds. So that's what we're going to be talking about. So metal complexes, I'm just going to start with kind of an introduction. They have completely different properties than what organic ones do. And one of those properties is that a lot of the time we get colored crystals out of them. Okay, so like this is, and hopefully you printed it off in color, but they're colored because of those transition metals. So we're going to talk about why that occurs, and how that occurs. So for gemstones, they are colored due to transition metals. Okay, and we'll get into, like I said, why that is. So the reason we get like red rubies and green emeralds is due to what's called crystal field theory. Oops. Moved me. Crystal field theory, and it has to do with really all of those S and D electrons, and what they're doing and how they affect each other. So rubies specifically have some of their Al3+ ions replaced with chromium 3+ ions, and those give rise to that red color. Emeralds, very similarly, some of their Al3+ ions in this specific compound is Be3 Al2 SiO3 6. I know it's a very complicated compound, but we're going to be looking at complicated compounds like this are replaced with chromium 3+ ions. Now you might be thinking, well, if they're both replaced with chromium 3+ ions, why is one red and one green? And the reason is because of crystal field theory. So their electrons actually do different things depending on all of the things that they are bonded to. Okay, so that's just one of many examples of where we see colored compounds based on metal complexes. Okay, so we're going to start talking about these complex ions. Things like this beryllium compound are considered complex ions because they've got multiple things attached to them. So another word for complex ion is a coordination compound, so AKA coordination compound. And those are molecules or atoms bonded to a metal. So like you can have whole molecules bonded to it. So definition is molecules or atoms bonded to a metal. An example is AgNH3 2+. And so what this is it's a silver that has two ammonia molecules attached to it. It looks like this. Whenever silver is in the vicinity of ammonias, they like to bond to that silver, and they share those those electrons in their like S and D orbital. So this is the complex ion. Okay. So there's a name for these attached molecules, like ammonia in this case. They're called ligands, or sometimes you might hear them called ligands. Those are the attached molecules. Okay, so there's a couple of different terms that we need to know. So complex ion or coordination compound, ligand, coordination sphere, and coordination number. These are all going to be important vocabulary terms as well. So a coordination sphere is the metal and all of the ligands bonded to it. Like we refer to that as the coordination sphere. So that's the metal and the total number of ligands bonded. Okay, the complex is the neutral charged salt. Okay. Okay, so how is that different? Well, if you noticed this coordination compound up here, or this coordination sphere, this complex ion is an ion. It has a charge of plus, and you can't just have positively charged ions existing. It has to be plus and a minus. So they have to be two things together. So the one with the other part is the complex. So it's the neutral charge salt. So like if it was this, it could be this Cl, like with a chloride ion. I just have to be balanced out, okay? So the neutral charge salt means it may have additional cations or anions, /anions that are not covalently bonded. So these are all sharing electrons. This complex has a bunch of covalent bonds, but since it's positive, there's probably like a chloride ion out here to balance it out. You have additional cations or anions, not covalently bonded. Okay. And finally, the coordination number is like how many really bonds are connected to that central metal. Okay, so coordination number is, in specific terms, the number of lone pairs donated, I'm going to put shared, to the metal. Okay, so it's like the number of bonds, i.e. bonds. And it is usually 2, 4, or 6. Okay, so things, it's not the number of things attached to it, it's the number of bonds, because some things actually require multiple bonds, which I will talk about a little bit later. So example number 1, I've got for this compound here. So this is a copper, and inside the brackets, I have 4 NO3, those are nitrate ions, right? And then outside the brackets, I have a sulfate ion. So this sulfate is not attached to the copper. That's how this name works out, okay? So determine the complex ion charge, the charge of copper, and the coordination number. Okay, so the charge on each thing, okay? So I want the charge of this whole thing first. That's the complex ion. Well, sulfate is a -2. So that means that whole compound has to be +2. So the complex ion charge is +2. Okay, that's one answer. Now I want the charge of copper. Well, if this whole thing is +2, NO3, 4, +2, then we can figure out what copper's charge is. These are nitrates. NO3 has a -1 charge. And since there's 4 of them, that means a total of -4 charge just from those nitrates. Now it has to be +2 overall. So in this case, copper has to be +6, because +6 and -4 would give you +2. So copper has to be +2, or sorry, +6 in this case. And then also the coordination number, that's the number of bonds of the things attached to it. So since there are 4 nitrates, the coordination number is 4. Number is 4. Okay, so I would like you to try example number 2 here for this cobalt compound to determine the complex ion charge, the charge of cobalt, and the coordination number. I would pause it right now. Okay, so I had 3 chlorides, so the negative ion is -3, so that means that this compound had to be +3. Now this is NH3. Notice it's not NH4 plus, it's just NH3. NH3 is not a polyatomic ion, it doesn't have a charge. So that means that none of these are charged that are onto the cobalt, so the cobalt must have been +3. And finally, the coordination number, it has, I have a picture over here, 1, 2, 3, 4, 5, 6 of the NH3s or the ammonias attached to it. So that means its coordination number is 6. All right, I'm going to bring back a little bit of VSEPR theory here now, and we're going to look at the shapes of these molecules. Okay, so if they can have 2, 4, or 6 things bonded to them, or that's where they're sharing, they have that many ligands attached to them. If it's 2, they're just going to be linear. If it's 4, there's going to be 2 options. So usually 4 things attached, we think tetrahedral. Now, sometimes though, if it has 4 things attached, it's square planar, and that's probably because it's got some extra electrons on there, right? So these are going to be the only 2 options for metal complexes. And then if it has 6 things bonded to it, it's going to be octahedral. So these are the only options for these compounds. Okay, so you don't have to remember all of the different shapes. These are going to be our only options for these metal complexes. Okay, so we're going to go a little bit more into these ligands really quick. Another word for a ligand is a chelate. Chelates mean they like, it's based on the word claw. So they chelate, or they kind of like grab onto the metal. You can kind of think of it that way. So chelates are another word for ligands. Word for ligands. Okay, it comes from the Greek word for claw. And so chelates are another word. So chelates or ligands can be either monodentate or bidentate. So mono meaning one, right? Now, when you think of dentate, you think of like teeth. And so monodentate means it is one toothed. Okay. That means it attaches at one spot. So it has like one thing that hooks onto the metal. So one toothed really means one bond. Okay, most of our ligands are going to be monodentate. Most. Okay, so these examples of these are like NH3. We saw those on the previous example. It can have chlorides attached to it. It can have cyanides attached to it. All of these are monodentate. Okay, so bidentate would mean two-toothed. And that means each of these ligands actually needs two bonds to that central metal, means two bonds. Okay, so what happens is like these are two examples of ones that need two bonds, or they need to grab on with like two teeth. This is the oxalate ion, which is C2O42 minus. And this one is a little bit more complicated. According to our organic naming rules, these are amines, right? This is called ethylene diamine. And instead of writing out all of the molecules, we usually just put EN for ethylene diamine. So both of these are the two that you need to know that are bidentate. So they need two bonds. So if you have one of these bonded to your central metal, that actually means it is coordinated in two places. So it has two bonds. Okay, so these take up two coordinations. Okay, so like we were talking about before, it's not the number of things bonded to the central atom for the coordination number, it's how many bonds it has to make. So bidentate takes up two of those, okay? And then polydentate is if it needs more than two. So of course, multiple toothed. Really the only one that you guys will come into contact with is EDTA. This is EDTA. Obviously, it's a very large molecule, which is why it has to connect in many places. This one actually connects in 4 places. And those are really the only ones that you guys are going to see when we start making these compounds.